Welcome to lecture 14, module 4. We have been talking about flow through soil, effect of flow on the stresses, etc. Now let us look at some real problems wherein we would like to study how the flow through the soil affects. So we call this particular phenomenon as seepage. We use the idea normally in the house. If you have a storage tank or a drain pipe, if the water is leaking from there and you see the patches on the roof or the wall, you call it as a seepage patch. In real life, seepage occurs whenever you want to store water. Let us say one of the most unique ones was the Godavari Anicut, which was built about 170 years ago. So there was a barrier put in. We call it as Anicut, which is built by Sir Arthur Cotton, which transformed whole of Konaseema, East Godavari, West Godavari. And then you find that by storing water in the river, let's say this is the river, and you build the barrier, so the water can be retained up to a certain height, and then take canals from here on the left and the right banks. You can use it for irrigation. This is fine. You are building a barrier across the river, so there can be no flow through the Anicut. But what about once you store water here, the water pressure is acting, there is always a possibility that water will flow below the barrier, Anicut in this case. Look at the Krishna barrier or barrage at Vijayawada. You have a concrete slab, then we have these pillars through which we put a gate, so that I can do exactly the same. Instead of having a earthen or masonry block on the river, we are putting a barrage. This is called a barrage. And we are storing water again. The possibility of flow below the barrage is very likely, and you have to address that. Third one, which is the most common one, whether you have a gravity dam or an earth dam, and storing water, the flow below and the flow through this is an earth dam. This is a concrete or masonry dam. For example, if you look at Nagarjuna Sagar dam, it is masonry dam, whereas Bhakra is a concrete dam. With concrete or masonry, there will be no flow or very little flow, but flow through the foundation is a serious issue. We need to address this. Another practical situation is when you have seepage into excavations. Nowadays, many buildings they are constructing with 2-3 basements. So if this is the ground level, they want to go 10 to 12 meters below the ground level so that they can get for car parking services. Now, if you have groundwater level here, above the bottom of the excavation, you can take measures to prevent seepage from the sides. But nothing can be made to prevent seepage upward. So the last situation where you deal with seepage in ground is flow into excavation. There are many more such issues, but what we are interested is how to study this flow in the soil. It can be usually 2 or 3 dimensional. You can see the flow is downward and horizontal. So let us see what is the basis on which you can predict how much flow is taking place, how much is the head at different points, what is the gradient, and what will be the effect on the structure. For example, here on the barrage and the gravity dams, you will have what they call as uplift forces. the water pressure can lift the barrage if you don't design it properly. Similarly here, you will find that the uplift force can cause some damage to this gravity dam if you do not take that into account in the design. So all these are the parameters that we need to study so that you design a proper hydraulic structure resting on or inside the ground. So seepage is a phenomenon of flow through the soil. So let's look at the particular phenomena, and we are talking of through, of course by that I mean through either one soil or several soils. We'll only concern ourselves with a two-dimensional problem. That means the flow is in the horizontal and the vertical directions. When you go to a more advanced one, you may also study a three-dimensional flow in general. So let us say you are looking at one of these situations where you said there is a anecut or a dam and you want to study the flow. So I would like to look at a small element here. This is the x-axis and the z-axis. I'll take a small point and then imagine a small element. The size of the element is delta x in the horizontal direction, delta z in the vertical direction. Let's say in the third direction, it's delta, delta y. And how does the flow take place? I'm interested only in the flow within the plane of the board, and I'm not interested flow perpendicular to it because it's a dam or anecut which is running into, let's say, 1 kilometer. So the water is there all over, so there cannot be a flow along the dam, but it will be across the dam. So please remember, it can be only in this direction, and we are not looking at flow along the anecut, dam, barrage, or excavation, whatever you have. So that is why we call it as a two-dimensional problem. I want you to visualize this element of size delta x, delta y, delta z, a small infinitesimal element. Let me enlarge that. So this is delta x, this is delta y, and this is dimension is delta z. Shall I call this as A, B, C, D, E, F, G, H. A, B, C, D is one plane, E, F, G, H is another plane in the direction delta x, and similarly if I look at it, B, F, G, C is a horizontal plane, and similarly A, E, H, D is another horizontal plane at a height delta z. Let us say the velocity of flow into the element is Vx. A certain amount of water is going inside the element. This is a very small infinitesimal element. Now these velocities need not be constant. They vary with distance. Velocity is a function of x and z. That is, the velocity varies with x direction, also in the y direction, because as you can see, where the gradient is high, the velocity will be very high. Once it travels, comes down here, the gradient is very small, it is losing head, and so the velocity will be smaller. So v is a function of both the distance coordinates x and z. So what I would like to see is how much water is going in and how much water is going out. So can I say the water is entering into the element with a velocity Vx, and the velocity changes by a small amount which is equal to the gradient of velocity or the derivative with respect to x times delta x. This is the gradient of the velocity with x, and this is the distance. So I calculate the velocity of water which is going out of the phase. Please remember, ABCD is a vertical phase through which water is entering into the element, and EFGH is another vertical plane through which the water is going out. The velocity with which water is entering is Vx. The velocity with which water is leaving the vertical phase is Vx plus the gradient of velocity with respect to x times the distance. If you want to calculate, you always multiply gradient with the length, so you get the change. Similarly, can I say the flow into the element in the vertical direction is Vz, and the flow out of the element is Vz plus the gradient of velocity in the z direction times delta z. What is the velocity with which water is entering into the element? Vz in the z direction. And what is the velocity with which it is going out? It Vz plus variation of velocity or gradient of velocity with z into delta zm. So I am multiplying the gradient with the distance delta z. The plane BFGC and the plane AEHD are separated by a distance equal to delta z. So these being functions of x and z, you are finding out how much is the rate. Now calculate what will be the flow. Flow is equal to, we have said, flow is equal to Q into area. So can I say now the flow into the element Vx into what is the area of the element? ABCD. Similarly, when I want to calculate the amount of flow going out, it is Vx plus delta Vx by delta x into delta x. And what is the area? EFGH. So the flow into is given this expression. The flow out of the element is given in this expression for the horizontal direction. Can I now add the flow into through the z direction? That will be equal to Vz, and the area of the element is BFGC minus Vz plus delta Vz by delta z into delta z into what is the area through which is going out? AEHD. Now we have to now distinguish two situations. One is called the steady state and the second is called the transient state. Steady state means it is continuing for all time, whether it is 1 day, 1 week, 1 month, 1 year, etc., which means it's continuously happening. If that is happening, can there be any water inside? Either it is increasing or decreasing, then this whole volume will increase. So in steady state, there will be no volume, net volume input into the element or out of the element. So here you can say delta V is equal to 0. There is no, you cannot accumulate water into the element. If you say it's accumulating, after 1 week it will be more, after 1 month it will be much more, and after 1 year it will be enormous. Or if it is decreasing, volume continuously decreases, that becomes a transient state. We will not study transient state now, we will only study the steady state. So in the steady state, the net volume into the element, net volume of flow into the element is 0. Please remember, whatever is going in will be going out. That's all it simply says. Volume flow into the element is equal to flow out of the element. Or can I say flow into minus flow out is equal to 0. So that's what we said. The amount of water flowing into in the x direction minus the amount of water going out in the x direction plus the amount of water going in the z direction minus amount of water going out in the z direction. The net volume is 0. Now let us try to find out what is the area of this element. AB, CD, AB is Z and BC is delta Y. So delta Z into delta Y will give me the area of this element. So let us now write Vx into delta Y into delta Z minus Vx plus delta Vx. What is the area? E of GH, again delta Z and delta Y plus now Vz. What is the area? B of GC. This is delta X, this is delta Y minus Vz plus delta Vz by delta Z. What is the area? AE, HD. This is AE is delta X, EH is delta Y. So we now know area, which is equal to these two. First Vx into this area, Vz into delta X delta Y gives you the amount of flow into the element. The second, these two terms give you the amount of flow out of the element. Now you can simplify this expression very easily. It's not a big problem. You can see that Vx into delta Y delta Z, we have minus Vx into delta Y delta Z. Similarly, you have Vz, velocity in the Z direction, into delta X into delta Y is the amount flowing in, minus Vz into delta X into delta Y. So I can simply cancel these terms and get a simple expression. We will have minus delta Vx. Now you have a delta X here, delta Y and delta Z. So you will have, similarly, you have cancelled these two terms. So we have the gradient times delta Z, delta X, delta Y is equal to 0. What do you find now? A very simple expression. If I know the gradients in velocity, how the velocity changes with distance in the X and the Z direction, I can multiply that with delta X, delta Y, delta Z. Similarly, gradient of velocity in the Z direction with respect to Z multiplied by delta X, delta Y, delta Z. You can see that you can cancel the negative sign, and this is nothing but the volume of the unit element, that's also constant. So I can simplify and say one of the simple equations that you can derive, the gradient of velocity in the X direction, delta Vx plus delta X plus delta Vz by delta Z is equal to 0 for steady state flow. That means there is no net change. If the 100 cc of water is going into the element, 100 cc is going out. If it is going 10 liters into the element, 10 liters will go out. This is how we study the long-term situation, and we find out how much flow is taking place. Please remember, the flow can change directions. What is entering in the X direction may go into the Y direction, or whatever is going into in the Y direction or Z direction can go into the X direction. So it can change, but the net flow is always, net quantity is always the same, which means the element does not have any extra amount of flow into the situation. Now this is a very simple equation. Now you can say Vx from Darcy's law is equal to Kx into gradient I in the X direction. So can I say K into delta H by delta X. Similarly, V in the Z direction is equal to permeability in the Z direction into the gradient in the Z direction. That will be equal to Kz. So I have the gradient in the Z direction you have the gradient in the x direction, multiply with the respective coefficients of permeability, and you will get the two velocities. Can we substitute here? So can I write delta by delta x, Vx is equal to permeability in the x direction multiplied by the gradient in the x direction plus the derivative, partial derivative with respect to z, kz I just simply substituted. This is what you call as the continuity equation. Please remember, you would have used in fluid mechanics too. The continuity of flow has to be maintained. So it is expressed by a very simple mathematical expression, which is gradient of velocity in the x direction plus the gradient of velocity in the z direction is equal to 0. Though it's a mathematical one, all you are saying is the amount of water going in is equal to the amount of water going out. Now, if I now substitute for the velocities in terms of permeability and the hydraulic gradient, please remember h is the total head. It doesn't depend on the direction. If I look at the head in the water, it's the same. So I'm using the same h. So I have derivative with respect to x of k into derivative with respect to x of the head, similarly in the z direction. If kx and kz do not vary with x or z, that means they are constants. If they are constants, can I take them out of the derivative? I can write it as kx, and now I'll have derivative with respect to x and another derivative. I'll get second derivative. Because kx and kz are not dependent on x or z. I have a soil medium here and I have built a dam. So whether I determine permeability here, anywhere, the values are same in either direction. We can also say, as a particular case, kx is equal to kz, what we call as isotropic medium. That means the properties are same in all directions. If kx is not equal to kz, we call it as an isotropic medium. It may happen in real life. Kx generally is greater than kz, and if that is so, we'll have to study that as a particular case or a special case. We'll now concentrate on this isotropic medium. So if you say kx is equal to kz, can I simply cancel these two and you will get what you say a simple, we call it as Laplace equation, because he is a mathematician who studied. Maybe you would have studied in your first year or second year mathematics. We sometimes write as, this is the symbol. When we say del square h is equal to 0, it implies the second derivatives in the two directions are 0. Sum of the second derivatives is equal to 0. This is what you call as a Laplace equation. This has application in all engineering fields. We have in flow through soil, we call seepage. The conduction of heat also follows the same equation, except instead of h, we'll have temperature. Instead of h, I use temperature. Similarly, conduction of electricity also follows the same equation. So we use the potential or say voltage V. So you can say this is one of the most universal equations in engineering, whether you are talking of civil engineering, mechanical, electrical, etc. So when you have a second order partially differential equation, you need obviously some boundary conditions. Unfortunately, there is no simple analytical solution. But we'll see how this can be applied. I want to illustrate how this can be done. First, let us take a one-dimensional flow situation. That will be easier. I'm looking at a simple flow problem. I'm looking at a simple upward downward flow through soil of a medium of length L. Suppose I measure Z from this top of the soil stratum. Let's see how this equation becomes. Now I'm looking at only the vertical direction. Is there any flow in the horizontal direction? Because the water reservoir is all here and uniform, so there will be only vertical flow, which means this term becomes 0, and we will have delta square H by delta Z square is equal to 0. What do we know about the boundary conditions? Suppose I say at the top, at Z is equal to 0, H is equal to whatever is the head, and at Z is equal to L, H is 0. I am now looking at this total head. So I'm at this point, if I take that, I'm looking at the net head. So head is dropping from H here to 0 because that's the net head loss. Now can you integrate this very easily? If I integrate once, delta H by delta Z is some constant A1, and now if I integrate again, H will become equal to A1Z plus A2. And I can use the two boundary conditions, saying that at Z is equal to 0, H is equal to, this term becomes A1 into 0 plus A2. So A2 is equal to H. And at Z is equal to L, H is 0. So 0 is equal to A1 into L plus A2, which is equal to H. So now that means A1 is equal to minus H by L. Now you can say the head varies H minus H into Z by L, which is a very simple way of looking at it, H into 1 minus Z by L. So at the top, the head is H. At the bottom of the flow, once Z becomes L, this ratio becomes 1, 1 minus 1 is 0, there is no head loss. So there is no net head here. So it's a linear variation of H. So maximum H and 0 here. So you have seen how this can be easily solved for a one-dimensional flow. If I want at any point halfway, so this is Z is equal to L by 2, then the head will be obviously Z at L, Z is equal to L by 2 will be simply equal to H into 1 minus 0.5 L by L. So that's head will be 0.5 H. You know that it's a linear variation. We have seen that earlier. H is 0, is equal to the total head here at any point. This is midpoint is point. If I take any Z, I can easily get from this expression. So head loss is linear in case of one-dimensional flow. It may not be linear in the case of two-dimensional flow, and that is what we will be studying later. But basically, if I want to study a two-dimensional problem, we need 4 boundary conditions. What are they? For example, here is the what we say is that along AB, the head is equal to H naught. Similarly, along CD, the head is constant, which is equal to the downstream one. The upstream head, downstream head. We also say the flow is bounded by the two mediums. Here is a hard rock. So the flow can be only within the medium. If I go far away, I can say that the head is constant along the depth, which is equal to H naught. And if I go far away here, the head is constant equal to H1. So this is how we try to define the four boundary conditions and solve for seepage through soils. We'll now actually find out a very simple graphical way called the flow nets. I'll discuss that in the next class, which without solving the Laplace equation, you can get the flow nets very easily. In order to illustrate this flow, you can also handle soil strata of different permeabilities. All that we do is we analyze each layer separately and satisfy continuity.